everyone. Welcome to lesson 6 on gases and stoichiometry. Today, what we're going to do is learn how to put together the information that we learned in our previous unit on stoichiometry with our gas laws, especially the ideal gas law that we learned about in this unit on states of matter. So just giving you a quick update on our map. So in the past, we've used mass and molar mass to convert between the grams of a substance and the moles of a substance. Well, today what we're going to do is we're going to learn how we can use the pressure, volume, and temperature measurements and our ideal gas equation to also get to that mole measurement. Remember that once we're in moles, we can go anywhere else on the map. So that includes moles of product and then grams of product or even a pressure of product. Since we're not learning anything new, instead, we're just learning how to implement what we already know in a new way. We're going to begin by looking at an example problem. So in this problem, we're combining ammonia gas and hydrochloric acid. So let's begin by writing out a balanced chemical equation for the reaction that occurs. In this case, it says that the ammonia gas has an initial temperature of 22 degrees Celsius. So what I'm going to do is list all of the givens underneath their respective substance in the chemical equation. Then we'll go back and look at what we have and decide how we're going to approach this problem. We continue reading, it says that it has a pressure of 750 mmHg. And finally, it tells us that the reaction occurs in a 10.50 liter container. And produces solid ammonium chloride precipitate. Calculate the amount of solid produced by the reaction. Notice in this case that they tell us up here in the problem that we have an excess of hydrochloric acid. So this is not a limiting reagent problem. The amount of ammonium chloride that we produce is going to be based just on the amount of ammonia that we started with. Okay, since we are provided with our initial information in the form of pressure, volume, and temperature, in order to calculate the grams of ammonium chloride that we formed, we're first going to have to identify the moles of ammonia that we start with. So to do this, we're going to use the ideal gas law and PV equals nRT. In our case, we're going to solve for the number of moles. Now, keep in mind, we cannot use temperature and pressure in their current units. So we're going to have to convert them into Kelvin for temperature and into ATM for pressure. So let's do that part first. When we take 22 degrees Celsius and we add 273.15, we'll get a final temperature of 295.15 Kelvin. Of course, we always know the value for R is 0.0821 liter ATM over mole Kelvin. We know our volume in this case because it was given to us in the problem as 10.50 liters. And finally, we know our pressure, but since our pressure is in mmHg, we're going to divide this by 760 to get 0.987 ATM. So if our original gas law is PV equals nRT, when we rearrange it to solve for the number of moles, we're going to get PV divided by RT So our pressure in this case is 0.987 atm. We're multiplying by our volume of 10.50 liters. We're dividing by our value for R, 0.0821, and our temperature. So when we're dividing, we have to make sure that we hit divided by in front of each of these numbers. So typing this part into the calculator, we're going to get 0.987 times 10.5 divided by 0.0821, but also divided by 295.15. So we wind up with an answer of 0.428 moles of ammonia. Now, this isn't our final answer. Instead, what this did was get us from our pressure, volume, and temperature that we had here up to our number of moles here. So now we're ready to move across from moles of A, which is moles of ammonia, into moles of ammonium chloride. So I'm going to start off with my 0.428 moles of NH3. Then, based on my balanced equation, I'm going to be able to convert from moles of ammonia to moles of ammonium chloride. That's a 1-to-1 mole ratio. So 1 mole of ammonia produces 1 mole of ammonium chloride. And finally, from moles of ammonium chloride to grams of ammonium chloride, so 1 mole of ammonium chloride. Now we have to get the molar mass for that. So if we open up our calculator, we have nitrogen, that's 14.01. We have 4 hydrogens, so that's 4.04, plus 1 chlorine, that's 35.45, for a total of 53.50 grams. So now I'm ready to multiply across. So I have 0.428 times 53.50. So I wind up with a final answer of 22.9. So remember, I'm limited to 3 significant figures. So 22.9 grams ammonium chloride. So the problem is done the exact same way that you would do a stoichiometry problem down here. However, instead of starting off with a mass in grams like we did in a typical stoichiometry problem, now we're starting off with some initial conditions of pressure, volume, and temperature because we're dealing with gases. Once you convert those into the number of moles of gas, everything lines up exactly as it would in a stoichiometry problem. Let's take a look at a second example. In this example, we're reacting sodium iodide with a sample of chlorine gas. Now, for accelerated honors students, you might be expected to predict that this is a single replacement reaction and write out both the products and their states of matter. For honors and CCP students, you'd be provided the equation, and you would simply need to balance that equation before you could begin looking at the problem. In either case, I'm going to begin by writing out the balanced chemical equation for this problem so we can continue. The next part of the problem says, the chlorine gas is initially sealed in a metal tank with an internal volume of 5.00 liters. So for chlorine, we have a volume of 5.00 liters at a temperature of 12.85 degrees Celsius. and a pressure of 1500.0 mmHg. The problem is asking us to calculate the mass of solid I2 product that forms as a result of this reaction. We are also told right here in the beginning that we have 10 grams of sodium iodide. Since we are provided the starting amount for both reactants, and since neither reactant is in excess, we're going to have to figure out which one of our two reactants will run out first. This is your typical situation with a limiting reagent problem. The only difference is this time, one of our reagents is a gas. So instead of giving you two different masses, we have the mass of one substance, and then we have pressure, volume, and temperature conditions for the second. Now, in order to do this, you're going to start by first balancing out your chemical equation. So we are going to put a 2 in front of the sodium iodide and a 2 in front of the sodium chloride. That will leave us with coefficients of 1 for both chlorine and iodine. Once you're set up your balanced equation, once you have identified where all of the different givens go in your problem, you're ready to begin. So in this case, I'm going to start off by looking at our 10 grams of sodium iodide. This part is going to be a traditional stoichiometry problem that starts off with mass, finishes with mass. We're going to use 3 fractions in order to get across. So in our first fraction, we're going to convert from grams into moles of a substance. So we're going to need to know the molar mass for sodium iodide. So first, the molar mass for sodium is 22.99 plus the molar mass for iodine, which is 126.90. That gives us a molar mass total of 149.89. We're going to put that number on the bottom so that grams of sodium iodide will cross out. In our next fraction, we're going to convert from sodium iodide into what we're looking for down here, which is I2. So using the mole ratio from the balanced equation, we have 2 moles of sodium iodide on the bottom. We have 1 mole of I2 on top. In our final fraction, we have 1 mole I2, and then we need to find its molar mass. So 126.90 times 2, which turns out to be 253.80 grams of I2. Now, in this case, we can simply multiply across, just like we would do in a stoichiometry problem. So we have 10 grams divided by 149.89, the molar mass, also divided by 2, because the 2 is on the bottom of our fraction, and then finally times 253.80 on top. We wind up with 8.47 grams of I2. Now, we will not know whether that number is the smaller or larger amount until after we perform a similar calculation using our chlorine gas. However, this time, instead of using mass to moles, going through molar mass, we have to use our conditions of pressure, volume, and temperature to get our initial number of moles of chlorine. So let's take a look at this. We were told that we have a volume of 5.00 liters we have a pressure of 1500 mmHg. But in order to convert that into ATM, we're going to have to divide by 760. So 1500 converting to ATM means dividing by 760. So we wind up with a pressure of 1.97 ATM. We're looking for our number of moles. We always have our value for R, which is a constant. And our temperature is going to be 12.85 plus 273.15 for a total of 286 Kelvin. We start off with our equation PV equals nRT. We know that we have to solve for N. So N is going to be equal to PV divided by RT. So N is going to be equal to our pressure, 1.97 atmospheres, times our volume, 5.00 liters, divided by the value for R, 0.0821 liter ATM over mole Kelvin, times our temperature, which in this case is 286 Kelvin. Typing this into our calculator, we have 1.97 times 5 divided by R, 0.0821, and then also divided by our temperature of 286. And we get an answer of 0.419 moles of Cl2. The only difference between these problems that we're learning today and the ones that we did back in stoichiometry is that first step. The only difference is now, instead of being given grams and going directly to moles using the molar mass, we're given these conditions and we have to use PV equals nRT in order to get to moles of our reactant. Once we get to this part, then it looks just like the equation did up here. So we're going to start a new line. This time we're only going to need two fractions because we're essentially starting off right here. So we have 0.419 moles Cl2. The two fractions that we're going to use, we're going to convert from chlorine into iodine. This time it's a 1-to-1 mole ratio. So 1 mole Cl2, 1 mole of I2. The last fraction will look identical to the one above it. So we'll have 253.80 grams of I2 for every 1 mole of I2. We can type this into the calculator. So we have 0.419 times 253.80. We get this answer, 106 grams of I2. So now we're going to compare these two numbers. The amount of I2 that we got using up all of our sodium iodide and the amount of I2 that we got using up all of our chlorine. Clearly, we have a lot more I2 here. So that means two things. Number one, this is our theoretical yield. The smaller amount is our theoretical yield. We will never get up to 106 grams of I2 because once we reach 8.47, all of our sodium iodide, the original 10 grams of it that we had, are used up. So this never happens. So let's cross this out so we don't accidentally use it anywhere else in our problem. So students want to ask all of the time, if we're just going to cross it out, why did we even bother doing it? Why did we calculate that? And the reason is simple. We only knew that sodium iodide was the limiting reagent, that it ran out first after we compared the two numbers. So without this number, we would have no idea which one was less. We could have done this calculation here, and this answer could have been 3 grams, and that would have been our answer. But here, because our calculation had a smaller amount for sodium iodide, that makes sodium iodide our limiting reagent. So this part here is our limiting reagent. Now, some of you may be asking yourself, why did we have to figure out a limiting reagent? The problem didn't ask us to find a limiting reagent, but you should know that anytime you see a problem where you're presented with the starting amount for both reactants, you are obligated to figure out which one of those will run out first. Okay, let's take a look at the rest of the problem. So at this point, the only thing that we have done is solve for, right here, calculate the mass of I2 that forms. Now, if you're an honor student or a CCP student, that's it. This problem is done for you. If you're an accelerated honors student, there's one more part that you need to figure out. So if we continue reading the problem, it says, assuming no change in temperature, calculate the density of chlorine gas after the reaction is complete. So now think about this for a second. You need to calculate the density of something. That means you need to know its mass as well as its volume. Well, the volume is given to you in the problem as 5.00 liters. So really, we just need to know the mass of chlorine gas that remains after this reaction is done. We have the moles of chlorine to start, so what we need to do next is figure out the moles of chlorine that are used up, because that will allow us to subtract and find the moles of chlorine and thus the grams of chlorine that are excess. So to do this, we're going to once again start with our limiting reagent, our sodium iodide. But this time, instead of going across the reaction and figuring out the amount of product, we're going to go right next door and figure out the moles of chlorine that were used. So to do this, I have 10.00 grams of sodium iodide. Remember that sodium iodide is our limiting reagent. That's why we're starting with this. Once again, we're going to go from grams of sodium iodide into moles of it using its molar mass, which is right up here, 149.89 grams of NaI. That's for every 1 mole of NaI. In our next fraction, we're going to go from moles of NaI, according to our balanced equation, which is 2, to moles of Cl2. Now, some of you may be wondering, why are we stopping at moles of Cl2 when ultimately we need to get to grams of Cl2? And the reason is this. Up above, we calculated the moles of Cl2 at the start. That was right here before any of our chlorine was used up. So what we're doing essentially now is calculating our moles of Cl2 used. We'll be able to use those two numbers in order to calculate the amount of Cl2 that we have excess. So typing this part into the calculator, we have 10 grams divided by 149.89 divided by 2. We get an answer here of 0.0. We're going to go with 3 significant figures, 3 or 4 actually, 336 moles of Cl2. Remember, this isn't excess yet, this is used. Now that we have the amount that we started with and the number of moles of Cl2 used, we can subtract these two numbers. So we have 0.419 moles Cl2 at the start minus 0.03336 moles of Cl2 used. We're going to subtract these two numbers. So when we subtract, we're going to keep our 3 decimal places right here. So we have 0.386 moles of Cl2 excess. Now, in this particular problem, they're asking us about the density at the end. So we need to get to grams per liter. In a different problem, they could be asking us about something else, maybe the new pressure inside the container. So in that case, we would use moles again. We would plug that into here and we would solve for our new pressure. So depending on how the problem is worded and what it's asking for, there are a couple of different ways that you could go. But in this problem, they're specifically asking for density. So now what we're going to do is we're going to take the moles of Cl2 that remain, and we're going to convert that into grams of Cl2. We have 0.386 moles of Cl2. This is our excess amount. We're going to convert this into grams. So 1 mole Cl2, the molar mass of 70.90 grams of Cl2. 35.45 off the periodic table. It's a diatomic, meaning it's a 2. So it ends up being 70.90. So now we have 0.386 times 70.90. And we wind up with 27 point, we have 3 significant figures, 27.4 grams of Cl2. Now, if you remember the formula for density, density is grams or mass divided by volume, which they give us in the problem. Remember, the container is not changing size as a result of this. So we're going to take our 27.4 grams of Cl2. We're going to divide it by our 5.00 liter container. We will get our density, which is equal to 27.4 divided by 5, 5.49 grams per liter. All right, that wraps up this lesson on gases and stoichiometry. I hope that you can see through the 2 problems that we've gone over that we didn't in fact learn anything new. Instead, we just learned how to take the ideal gas law and substitute it into what we already did, what we already learned about back in our stoichiometry unit. Hope everyone has a great week. If you have any questions, please reach out through Schoology, send me an email, or stop by office hours on Thursday. Thank you very much, everyone. Have a great week.